This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy. We go deep and lightly surface the big ideas. Welcome back. Today we're diving into some fascinating material, really a huge step forward in quantum computing.
It really is.
Yeah.
And the scale involved.
Yeah.
It's almost hard to wrap your head around.
Right. So the hook that grabbed me was this. A quantum machine, just 300 qubits,
Yeah, quantum bits.
could theoretically hold more information simultaneously than all the particles we know of in the universe.
That sheer potential, that exponential power, that's always been the dream, hasn't it?
Absolutely. But it's been just that, a dream, because the big hurdle was always, well, how do you keep these things stable?
Exactly. How do you keep such delicate systems running long enough to actually use that incredible power? It's been the fundamental bottleneck.
And that brings us to our mission for this deep dive. We're looking at a major breakthrough from a Harvard-led team working with MIT and Quera Computing.
A big collaboration.
Yeah, and they didn't just build a big system, though
Yeah.
they did that too, over 3,000 qubits. But the real news is they figured out how to run it continuously.
For a long time, yeah.
Yeah.
That's the key.
So we need to unpack how they cracked that problem, how they overcame the biggest operational issue. Just keeping the machine running, duration.
It's what could potentially move quantum computing from, these amazing lab curiosities towards being actual reliable tools.
Okay, so maybe just a quick refresher for everyone on the core quantum advantage.
Sure. So classical computers, they use bits.
Yeah.
Simple, right? 0 or 1.
On or off.
Exactly. But qubits, because they use these tiny atomic properties, they can be 0, they can be 1. Or, and this is the crucial part, they can be both at the same time.
That's superposition.
That's superposition. And it leads to this incredible scaling.
Right, because in classical computing, if you double your bits, you roughly double your power.
More or less. But with quantum, because of superposition and another effect called entanglement, adding qubits doesn't just add power, it multiplies it exponentially.
Okay, so the power is immense, theoretically. Why haven't we seen massive quantum computers everywhere, then? Our sources really point to one main culprit in these neutral atom systems: atom loss.
Yeah, atom loss, it sounds almost mundane, but it's been a massive headache.
So the qubits, the individual atoms, they're held in these super delicate traps, right? Like laser beams.
Tiny optical tweezers, yeah. Very precise, very fragile. And the atoms, well, they just escape sometimes, or they lose their quantum state, the information they're holding.
Which basically meant that previous experiments were like quick snapshots, one-shot deals.
Pretty much. You'd set everything up, run it for a tiny fraction of time before too many atoms were lost, then you'd have to stop, reset, reload all the atoms.
That sounds incredibly inefficient. A huge bottleneck.
It absolutely crippled progress towards longer computations. You couldn't run complex algorithms.
Okay, so let's get into the specifics of this breakthrough then. The Nature paper details a system. How many qubits again?
Over 3,000 qubits, which is already impressive, scale-wise.
But the headline number isn't just the qubit count, it's the runtime. They kept it going for
Over 2 hours.
2 hours compared to, what, milliseconds or seconds before?
Exactly. And critically, the way they designed it, they think it could potentially run indefinitely, continuously.
Wow. Okay, so the continuity is the real story here.
It really is. One of the lead researchers, Mikhail Lukin, even said that this continuous operation might actually be more important in practice than a specific number of qubits.
And you can see why when you look around, like our sources mentioned another team, Caltech, right? They had a paper around the same time.
Yeah, they reported a system with even more qubits, I think over 6,000.
6,100, yeah. But the catch.
It could only run for less than 13 seconds.
Okay, so that contrast, 3,000 qubits for hours versus 6,000 for seconds, really drives home why just having more qubits isn't enough. You need them to stay there and stay working.
Precisely. It's like the difference between having a super fast car that runs out of fuel in one lap versus a slightly slower car that can run the whole race.
And this idea of continuous operation led to a really interesting framing from Lukin. He described the system becoming, what was it?
He said, we can literally reconfigure the atomic quantum computer while it's operating. Basically, the system becomes a living organism.
A living organism. That's quite a metaphor. It implies self-repair, adaptation.
And it does. It suggests they found a way to, heal the system on the fly. replacing lost atoms without shutting down the whole process.
So how did they do it? What's the engineering magic behind this living quantum computer?
Well, they basically built a new kind of architecture, a zone system specifically designed to feed new qubits in constantly and quickly, tackling that atom loss problem head-on.
Okay, zoned. So different areas doing different jobs.
Exactly. A
Yeah.
key part is having a high-speed preparation zone that's separate from the main computing zone where the qubits are doing their work.
Let's break down the mechanics. What are the tools they're using to shuttle potentially millions of atoms around so fast?
It comes down to two main things. First, for moving large numbers of atoms from a source, like a reservoir, they use what they call optical lattice conveyor belts.
Conveyor belts made of light.
Sort of, yeah. Think of waves of light pushing the atoms along. Then, for the really precise work, grabbing individual atoms and placing them exactly where they need to go in the array.
That's the tweezers you mentioned.
Right, optical tweezers. These are very tightly focused laser beams that act like microscopic tractor beams for single atoms.
Okay, so you've got bulk transport and precision placement. But the key to running continuously must be the speed of replacement, right? How fast can they cycle these atoms?
The speed is absolutely critical. They can load atoms into the tweezers at an incredible rate, up to 300,000 atoms per second.
300,000 per second.
Yeah. And then, once those atoms are prepared into the qubit state, they can maintain a continuous flow, a flux, of over 30,000 initialized qubits every second.
30,000 usable qubits per second flowing into the system.
Correct. And even when they do more complex sorting, arranging them into perfect defect-free blocks, say, batches of 600, they can still manage 15,000 qubits per second.
That's still incredibly fast. So over the 2 hours they demonstrated, how many atoms are we talking about cycling through?
The paper mentions over 50 million atoms had cycled through the system in that 2-hour period.
50 million. That's staggering. But wait, doesn't moving all those atoms around, all that laser light for the tweezers and conveyors, doesn't that create a ton of noise? Heat? Wouldn't that disturb the working qubit?
Yes. That is the multi-million-dollar question, isn't it?
Yeah.
How do you do all this maintenance without destroying the fragile quantum states you're trying to preserve?
Right. Seems like you'd solve one problem, atom loss, just to create another, decoherence.
And that's where the cleverness of the architecture really comes in. First, how they built the main array. They did it iteratively, section by section.
How many sections?
They built the big 3,240 site array in 6 segments. They call them subarrays.
Yeah.
And assembling the whole thing took only about half a second.
Okay, built-in segments. How does the continuous maintenance, the healing, work then?
It's a constant rotating cycle. Roughly every 80 milliseconds, really fast, the system identifies the subarray that's been sitting there the longest.
The oldest one.
Essentially, yes. It ejects those atoms and instantly refills that segment with a fresh batch, newly prepared from the loading zone.
So it's like constantly patching the array piece by piece, faster than the atoms can naturally decay or escape.
Exactly. This rapid targeted replacement is what let them keep over 3,000 atoms active for those 2 hours. Way, way beyond the typical lifetime of maybe 60 seconds you'd get just holding them in tweezers alone.
Okay, the mechanics are brilliant, but it still brings us back to that core quantum problem, coherence. How do you run this intense reloading operation right next door to qubits that are actively computing, holding delicate superposition states without wrecking them?
That's the crux of it. You've got loading, transport, preparation, all involving lasers and atom manipulation happening concurrently with the quantum operations. And any stray light, any vibration can cause decoherence, making the qubits lose their quantum magic.
So they needed protection. Shields up.
Shields up indeed. They implemented 2 main layers of protection, a physical one and a more, let's say, quantum level one.
Okay, start with the physical. What did they do architecturally?
Remember the different zones. The big source of noise is the very first stage, where they initially trap a cloud of atoms. It's called a MOT, a magneto-optical trap, and it uses intense lasers.
Bright and noisy.
Very. So to shield the main quantum register from that initial noise, they used a clever angled design for the transport system, the conveyor belts.
Angled. How does that help?
By using a tilted dual lattice setup, they physically blocked any direct line of sight between the noisy MOT area and the area where the qubits were being stored and manipulated. Less stray light could leak across.
So, geometry as noise cancellation. Clever. What was the second layer? The more quantum shield.
That was a technique they call qubit shielding. This deals with the more subtle noise, the scattered photons bouncing around from the nearby loading and transport of new atoms right next to the working atoms.
How does that work? More lasers.
Yes, but a very specific kind. They used light near a particular wavelength, 1529 nanometers, shone onto the stored working qubits. This light effectively adjusts the energy levels of those qubits slightly.
Okay, light shifting. What does that actually do for the qubit? How does it protect it?
Think of it like tuning a radio. The noise, the scattered light, is like static at a certain frequency trying to interfere with your station. The 1529 nanometer light dynamically retunes the qubit's energy levels so they're no longer sensitive to or resonant with that specific frequency of noise from the nearby operations.
Ah, so you make the working qubits effectively deaf to the noise being generated right next to them during the reload cycle.
That's a great way to put it. You create this dynamic temporary shield that protects their quantum state, their coherence, from that specific disturbance.
And did it work? Did the measurements show the coherence was preserved?
They did. It was quite successful. They measured the coherence time, technically the T2 at E2 time, how long the superposition lasts. And with the shielding active, it recovered to about 1.09 seconds.
How good is that?
It's very close to the ideal reference time of 1.34 seconds they measured in a completely quiet, undisturbed setup. So the shielding restored almost all of the coherence that would have been lost due to the concurrent reloading.
That's impressive. So they managed to keep the array full and keep the qubits in their quantum states, even the really fragile superposition ones, while all this maintenance was happening right beside them.
Exactly. They showed they could sustain the storage zone with qubits ready for computation, potentially indefinitely, because the reloading cycles in adjacent subarrays didn't ruin the state of the qubits in the working subarrays.
This feels like the moment it shifts from a cool science experiment to a potentially viable technology roadmap.
I think that's fair to say. It addresses a fundamental barrier to scaling up.
So let's synthesize this. For you, the listener, what's the big takeaway here? What does this continuous operation, this coherence protection, actually enable?
The big picture is that this architecture, this combination of continuous operation and proven coherent shielding, it really lays out a practical path towards fault-tolerant quantum computers. That's the holy grail.
Fault tolerance meaning the computer can actively correct errors as it runs.
Precisely. And you need long-run times and stable qubits to even begin implementing effective error correction.
So what's the potential impact then if we get fault-tolerant machines based on this kind of continuous platform?
Well, the projections are pretty staggering. The team suggests this could enable quantum computers to perform billions of quantum operations in a single run.
Billions compared to maybe thousands or millions now.
Right, and running not just for seconds or minutes, but potentially for days.
Okay, and if you have that kind of sustained quantum power, what problems can you tackle?
Oh, the list is long. Think about designing new drugs and materials at the molecular level, something classical computers struggle with. Complex financial modeling, optimizing huge logistical networks, potentially revolutionizing AI, and even things like building vastly more precise atomic clocks and sensors.
So science, medicine, finance, technology, a broad impact.
Definitely. It unlocks a new regime of computational power.
We really have arrived at that living organism computer, haven't we? The chip that heals itself and just keeps going.
We have. It's a paradigm shift.
And that brings us to a final thought, something for you to chew on.
If the hardware problem of continuous operation is maybe not solved, but has a clear path forward, what's the next big challenge?
The machine can run continuously now.
Right. So if you have this non-stop fire hose of quantum information processing, the bottleneck shifts. Now the pressure is on the software, specifically the error correction protocols.
They have to be fast enough and good enough to keep up with a machine that never needs to pause.
Exactly. How fast does your error checking and correction need to be to guarantee reliable results from a system that's perpetually running and potentially making errors? The sources hint that these improvements might eventually allow for hundreds of logical error-corrected qubits with incredibly low failure rates, maybe 10 to 8.
But getting there means the error correction has to be incredibly efficient.
That's the next frontier, matching the speed of error correction to the speed of this continuous quantum operation.
A fascinating challenge ahead. Thanks for walking us through this incredible engineering achievement.
My pleasure. It's exciting stuff. Thanks for listening today. 4 recurring narratives underlie every episode: boundary dissolution, adaptive complexity, embodied knowledge, and quantum-like uncertainty. These aren't just philosophical musings, but frameworks for understanding our modern world. We hope you continue exploring our other podcasts, responding to the content, and checking out our related articles at helioxpodcast.substack.com.